Great. All right, so I'm Slatkin again. I'm a software engineer on the Google App Engine team. Today we're going to be talking about building scalable web apps with Google App Engine. This is a more advanced course, session that we're having here. If you're familiar with the App Engine system, data store, and APIs, that's really going to help a lot. I'm going to try my best to go slow. I have trouble doing that sometimes, so please tell me, just yell. Feel free, okay? Tell me. Okay. So, all right, so here's the agenda of what we're going to talk about today. We're going to talk about using the Python runtime effectively. We'll talk about numbers that everyone should know and what that means. Then we'll talk about tools that App Engine provides you for storing and scaling large data sets. And then we'll go through some examples of actually scalable apps, some common ways to scale apps, and both a distributed counter and a blog example. Okay, so let's just jump in. So the first thing is to remember, this isn't just App Engine, this is kind of all web development. Prevent repeated wasteful work. So don't do it twice if you can do it just once. Kind of simple idea. So in Python, what that means is, don't reload your modules on every single request. Python is an interpreted language. There's an overhead to loading modules and executing them. Now, we do the best we can to optimize this in a lot of different ways. And so it's best that you take advantage of this. Otherwise, every request that comes in will have to reload your modules and pay that upfront loading cost every single time. So the simple thing you can do is you can reuse main. So if you define a main function like this, here it's just like in my example I did in the last presentation, you can define a main function and then run your web application from inside that function. Now what this is doing in the back end is it's actually loading your module, executing your application, and then if another request comes in, we look for the main method, and if it's there, we call it. So we don't have to reload your module. We just figure out that it's already loaded and we reuse it. And in this way, it's very much like some of the other interfaces, like fast CGI and some other things like that. We keep as much state in memory as we can to make it so you can reuse it, and that significantly improves your performance. Again, one of the other things is you want to prevent yourself from loading huge modules. So here, you can also lazy load big modules. So lazy load means don't load it until you absolutely need it. So you may have some very complicated Python module that requires 2 seconds to load. And you only need it once an hour, something like that. So don't load it until you need it. We have my expensive operation. Import the big module then. Just wait. Python's very good at this. It's very good at doing late loading of modules. And you can use this to your advantage. And the other thing that's interesting is that in Python, if the big module has already been loaded, then that's a no-op. It does nothing. So it's not going to pay that cost. It's just very fast. The other thing is, in Python, so as Pete was saying in the last presentation, we have something like 95% of the standard Python library and all the modules that are contained within it. We preload those modules. So preloading, we have them loaded into every Python instance so that the cost of importing those modules is none, basically. So take advantage of built-in modules. They're really fast. There's a lot of them. Python comes with batteries included, that's what they say. So, take advantage of the preloaded modules. So then, kind of going on, that was with Python. Now this is with data. So you want to, so here's some ways to avoid waste with data. So first of all, avoid large data sets. If you're pulling down 1,000 entities from the data store, 1,000 rows, and then doing some sorting and filtering in memory, that's wasteful. So make the data store work for you. Structure your queries in such a way that you're not wasting any time. Another way to think of this is use every entity you retrieve. If you retrieve it from the data store, use it. And if there are entities that you throw away, Change your query. Optimize your code as much as you can. Optimize your queries the best you can so that you don't waste data. And also avoid repeated queries. So your home page may have, it might be the main page that everyone accesses, like a main page on, like say eBay or Amazon that lists the same thing for everybody. That's running the same query again and again and again. That's really slow, very wasteful. So avoid that. Up until recently, we supported something called incoherent caching. It's caching inside the Python environment. And that's very similar to how fast CGI works. But as of 2 weeks ago, we released memcache support. So memcache is a shared cache between all instances of your Python runtime. So it's a coherent cache, a global cache. If you haven't heard of memcache before, I suggest you read about it. It's awesome. And it's a huge performance win. So here's a really simple use of it. Memcache lets you get and set key value pairs. So here I say, okay, get my results from memcache. If there are no results, then do a query and add the results to memcache. And then on the right side it says, store those results for 60 seconds. So that means they'll be cached for 60 whole seconds, so that every request that follows for 60 seconds does no work, no querying. It just pulls from the cache and it's done. So it saves a lot of work. And sites like Amazon and Google and every big site out there rely on caching like this in order to scale. So memcache gives you that out of the box. This is available for all applications today. So let's talk about numbers that everyone should know. So this is kind of a funny, numbers everyone should know. What does that mean? So you should know your birthday, that's one. But at Google, numbers everyone should know is something that Jeff Dean came up with. So Jeff Dean is kind of one of our distinguished engineers, one of the most well-known and most impressive engineers at Google. So he came up with this thing called numbers everyone should know. And what it explains is how to think about latency, performance, and optimization. And numbers everyone should know includes everything from the cost of a branch misprediction in an actual processor, all the way up to sending a packet halfway around the world, and how slow everything in between is. So that's really interesting when you think about performance. So let's talk about numbers everyone should know for App Engine. So first of all, writes are expensive. This is true for almost every other application platform in existence. It's also true for App Engine. The reason is that the data store is transactional. So when you do a write, you are actually hitting disk. You're writing to disk. And the reason is transactions. For standard ACID transactions with consistent semantics, you must have disk writes on the write. And a disk access means a disk seek. So disk seek is actually the head on the hard drive moving, right? And the rule of thumb is that that takes about 10 milliseconds. Okay? So simple math. 1 second divided by 10 milliseconds. We get 100 disk seeks per second, maximum. So that's a very rough estimate. But you can think of the limit of App Engine, for one single record, one single entity, you have a kind of a max throughput of 100 writes per second. Now, it can be a lot better than that. And it can be a lot worse. It depends on the size and shape of your data. Size meaning, how many megabytes your entities are. Shape meaning how many properties you have. Are your properties indexed or not? Stuff like that. And you can improve it. If you do work in batches, doing operations on multiple entities at the same time, you can lower the cost and actually get more throughput. But the key takeaway here is that writes are expensive. The good news is that reads are very cheap. So reads don't have to be transactional. Reads just need to be consistent. And that's a very important distinction. And so in Bigtable, this is kind of describing how Bigtable works. We read data from disk, and then Bigtable caches it in memory. And then all subsequent reads come from memory. So we can very, very, very quickly serve or retrieve data. And the reason is that we only care that the data is consistent. We don't have to actually transact for a read, like we said. So again, the number everyone should know. Estimated rough estimate is that it takes about 250 microseconds to copy 1 megabyte of memory from one part of memory to another part. So to do that same back-of-the-envelope calculation, 1 second divided by 250 microseconds is about 4 gigabytes per second of maximum throughput. So for a 1 gigabyte entity, that's 4,000 fetches per second. That's huge. It's 40 times more than the write throughput. Okay? So reads are very cheap. They're ridiculously cheap. Okay, so let's talk about some of the tools that App Engine provides for you to store data. We went over some of this in the previous presentation, but I'm going to dive into specifics. The first thing that we have are entities. So entities are the fundamental storage type in App Engine. Entities are a set of they have a set of properties which are key value pairs, and each property has a type. So you saw a date-time property, string property. We have a whole bunch of other types. We also support semantic types, like a geographic point is a native type. And these are types that are taken from GData types. And most properties are indexed, and they're efficient to query on. Other properties are not indexed, because you're going to store a lot of data in them. And the big thing is it's schemaless, so you can add properties whenever you want, and you can take them away. So we're not rigid in that way. But the data store is a lot different than kind of a traditional relational database. So it's good to think of it as an object store, not a relational database. So, think about kinds, entity kinds. Think of it as model classes. Think of them as just like object-oriented classes in Python. And think of entities as object instances, as opposed to rows in a table. Like tables and rows, think of it as classes and instances. And then you can define relationships just like you can with object-oriented systems. You have a reference property, and it provides a relationship between entities. And to do that, it uses keys. And so we'll get into what a key is, but it lets you represent one-to-many, many-to-many, and many-to-one relationships. So you can do all that. But I need to stress again, it's best to think of it as an object-oriented style database. And that's a big change for a lot of people. So what is a key? So a key corresponds to the big table row for an entity. So I don't know how much you know about Bigtable. There's a great paper on it that you should read that explains what Bigtable is, how it works, why it scales. And if you search for Bigtable paper on Google, I think it's the first hit. But in the end, Bigtable is just kind of like a distributed hash table. And it has a bunch of properties that make it faster in a lot of ways. And for keys in App Engine, it's kind of like using Bigtable as a distributed hash table. So you do a get with a key, and it's very fast. There's no scanning to do. You just find the right row in Bigtable, copy the data, and you're done. So just like a hash table lookup. But there's some limitations. You can only have one ID or key name per entity, so that's one unique identifier for an entity. You can't change that unique identifier once you put it in the data store. And that unique identifier can only be about 500 bytes in size. So we also provide transactions. These are ACID transactions. Those are the standard transactions. So that means atomicity, consistency, isolation, durability. These are real transactions. But the big difference is that we don't allow for queries of transactions. So a lot of traditional databases, they'll let you lock a table and then query over it, and then do something after that, and then unlock the table. That doesn't work in App Engine. It's part of our scaling models that we don't allow for that. So the way that we let you do transactions is with get and put. And so you retrieve a key, you retrieve an entity by key from the data store, and then transact on it, and then put that key back in. So the common practice you see is you see someone do a query and find the data that they want to use. Then they do a get to retrieve, then they start a transaction. They do a get on that data again, modify it however they need to, and then put it back in the data store. So there's a little bit of waste there depending on how you do it, but in a lot of cases it's just as efficient. And that's what lets us do this wide scaling that I'm going to explain. So one of the things though is that if you can't do a query and transaction, then how do you provide a consistent view? How do you know that the data you're looking at is consistent? So we'll get into that later. That's kind of the first question that popped in my mind when I heard about this. So I'll explain in just a little bit. So getting more into details, and this is where it starts to get very technical, so tell me if I need to slow down. One of the things about the data store is that we have something called entity groups. Entity groups are very closely related entities that are actually stored logically and physically close to each other, and sometimes on the same machine. So let's just take advantage of locality to optimize accesses of these entities. And entity groups also define transactions. So in a relational database system, you have row-level locking, you have table locking. That's the common way of doing it. In the data store, you define transactions with entity groups. And so each transaction can only happen on one entity group at a time. And then, so then an entity group consists of many entities. Each entity can only be in one entity group. And so then when you lock an entity in the group, you lock all of it, everything in that group. So it's kind of like a table lock. But you can have many different entity groups. And the entities can be of any type. So they're kind of like, you can have kind of many different pieces of data that are separate from each other, that are transactionally separate from each other. And I'll explain more of what that looks like. And that's kind of the core of my talk, is explaining how that works. But it's very interesting to understand this, that so within an entity group, which consists of a number of entities, we serialize writes. That means writes all happen in a row. And that's why you have a maximum throughput, roughly, of 100 writes per second, because we have to serialize them to guarantee transactionality. And unlike a standard relational database system, it's not a traditional lock. You don't lock the table and then operate on it. It's actually much more competitive. You have multiple systems working at the same time, attempting to finish their transactions independently. Whoever finishes first wins, and that's who commits the transaction. The other people have to roll back and try again. So there's much more contention in that way, but it also allows you to scale. So then the other thing is that, so I said that entity groups are a set of entities that are related to each other. The way that you define them is with a hierarchy. So every entity can have a parent. It's like a tree, okay? And entities that don't have a parent are root nodes. So each root node is a separate entity group. It's a separate set of transactions. It's independent. And it has its own throughput limitations. Okay? So then you can, and within an entity group, you can have a hierarchy that's many levels deep. You can have the parent node, the root node, then you have children, then grandchildren, and great-grandchildren, and so on, full tree. But what's interesting is that if you lock a grandchild down here, transactionally, you lock the entire entity group. You lock its parents, all of the siblings, everyone, the whole group, the whole tree is locked. That's kind of surprising. So you might think, oh, hierarchy, file system, XPath, right? Sometimes, maybe, but it's more complicated than that. So be careful. So the good news is that the data store scales wide. So each entity group has serialized writes. And each entity group is limited in its maximum throughput. but there's no limit on the number of entity groups you can have. So you can use all of these in parallel, and you can have each one of them transacting in parallel. So you can have one set of entities here, another set of entities, and then so on, each transacting in parallel, each with a maximum write throughput. So it looks like this. So we have a root node, we have child nodes, and we have 4 separate transactions happening here. Each one of these can have, like I said, roughly 100 writes per second. And you can have hundreds of these, all happening at the same time, in parallel. And that's where you get scalability. This is what Bigtable does very well. This is what the data store and Bigtable give you, and this is the key part of our scaling. It's scaling horizontally. So some pitfalls, though. A lot of people say, well, I want to transact on all of my data. So they just put everything in the same entity group. Well, that's not good, because then every time you do a write, you're locking the entire database. So that means that you have a lot of contention. If you're doing a lot of writes, you have a lot of people attempting to access the same data, and they conflict. And so then you get failed transactions, okay? And then that means you get errors in your application. So the bottom line is, if you don't think about your writes and your write throughput, that's really bad. You're setting yourself up for failure. You need to think about your usage patterns, and you need to structure your data and your writes specifically to match your usage patterns. So think about writes, think about how it affects the performance of your application, and structure your data to match. Okay, so the good news, finally some good news. The good news is that you can query across entity groups without serialized access. So remember how I said before, reads are not transactional, they're just consistent. That's what we're talking about here. So when you do a query, you get a consistent view across all entity groups. There are no visible partial commits. All you see is each entity group is the latest version of that entity group that's been committed. So you see the latest transaction that finished, that's the version you see. If there's a transaction that's currently processing, you don't see that. You don't see a partial information. You only see what's been committed. And so that's how we provide a consistent view. Okay, cool. So now we're going to go into some examples. It's a lot. It's easy to talk about this, but it's a lot more useful to see it in action to understand what's going on. Do we have any questions so far? Just blank stares. Everyone's confused. Okay. Yeah. All right. So what is a counter? What is a distributed counter? What am I trying to do here? So let's say you have a website and you're trying to do a poll. Who's your favorite, Nintendo character? Mario, Luigi, Toad, whatever. So you can have, who's your favorite athlete? You're trying to do a polling website. That's an example of a counter. Everyone votes for their favorite thing. So that's kind of a simple example, and it's something that people talk about a lot. And it's actually an anti-pattern. Okay, so there are patterns and there are anti-patterns. Anti-patterns are things that App Engine is not suited for immediately. Okay, so this is something that everyone needs, but it's actually hard to do correctly, and I'll explain why. So the first thing people say is like, oh, I need to have a poll. So if you're using SQL, every time someone votes, I write to a table, and then to find out the different votes, I do count. I find out the count for each different vote, group by, all that stuff. Okay. But Bigtable doesn't know counts by design. That's the point. We just scale wide. We have no idea how many entities you have. So if you want to figure out a count, it's big O of n, where n is the number of entities you have. SQL, it's O of 1, big O of 1. And that's just because of the way that Bigtable works. We have to scan every row to give you a count. So when people hear this, they say, oh man, that's different. Well, I'll just do this. I'll create a counter model, and it'll have the count as an integer. And then what I'll do is that every time someone votes, I'll grab the counter, and I'll transact on it, and I'll update the count, and then I'll commit the transaction. The problem is that if there are frequent updates, then that's high contention. And those writes are transactional, and they're serialized, and they're slow. And so you get failures. So I'd like to highlight at this point that this is a fundamental limitation of distributed systems. This is not just an app engine problem. It's a fundamental problem of distributed systems. Big tables running on thousands of machines. When you have global data, like a counter, you're sharing that information across the whole serving infrastructure. Okay? Now, that's global data. Now, what's local data? For contrast, local data is like your Gmail account. It's yours. It runs on these servers over here, and then mine's here, and then someone else's is here, and it's horizontally scalable because I don't need to read your email. Okay? So we have localized data that we don't share. But with a poll, that's data we share across all entities, across the whole system. And that's just a fundamental scaling problem in distributed systems. But it's something you need a lot of the time. So how do you do it? The big part here is that, so it's global data, which means everyone needs to write to the same entity group. So that's high throughput, high contention failures. Making that very clear. That's why it's a problem. So what we're going to do is really simple. We're going to partition the counter into pieces. Before we had this on the left, we had this single counter. Now we're going to split it into 3 or more, sharding it, partitioning it, whatever word you want to use. And the sharded counter will then split our data into multiple entity groups. And by doing that, we have a higher write throughput. So what we're doing is, if each entity group can do 100 writes per second, then we're going to have 3 of them here. So then we can do 300 writes per second. Now we can have 10 of them, then we're doing 1,000 writes per second. So let's just scale horizontally the counter, which is what you need for scalability. So to do this, what we do, we have 10, let's say we have 10 entities. We pick one at random, and then we transactionally update it. We add 1 to it. Then when we want to find out the total count, we query all of them, and then add it all together. And that gives us the count. It's a simple idea. And that reduces the contention by 1 over n, where n is the number of shards, number of partitions. And you can change the sharding factor pretty easily. So the number of shards you have, number of partitions. So here's some models that do this. We have a counter config. A configuration has the name of the counter and the number of shards. So it defaults at 1. Then we have the counter itself, which has a name and then the current count. So the current count. So, okay, very simple, just like before. So let's look at some code. So if we want to get the count, we do a query. We get all the counters with that name. We add them together, and we return the total. And this works because we have a consistent view across all entity groups. So gives us the accurate total. It's pretty simple. Here's a retard if I go slow. Don't worry. So this is for incrementing a count. So I'm going to use a little mouse here to make sure you can see. All right, so first off, we retrieve the counter configuration, and we insert it. We use getter insert. That means insert it if it's not already there. So we get a config. Then we define a transaction function. And in this, first we start off, we use random, we pick that random shard. So one of them, we pick one. Then we determine the shard name. Then we grab the counter object by the key name. And we look at the counter, and if it's none, which means it doesn't exist, then we create it. So we start the counter at 0. Then we take the counter we have, either from before or the new one. We add 1, and then we put it back in the data store. So let's put it down here. And then we run this in a transaction. So if at any point during the transaction it fails, we'll roll back, try again. And it'll retry until it gets committed. Okay. Now, we can make this even faster. So memcache is what I was telling you about. It's really fast. We can use memcache in this case. So here's a really clear use case. We checked for memcache, we looked for the total. If there's no total, then we do the query. And then we add it to memcache. So, and then we return the total. So this puts the data in the cache, so we're just quickly always accessing the cache instead of actually having to hit the data store. So that makes our reads very, very fast. Now we can actually do the same thing for writes, believe it or not. So here's that same code again. And you'll see at the bottom there's something called memcache.increment. Okay? And so after our transaction completes, we've updated the counter. We can tell memcache atomically increment this cache variable. So that lets you actually update your cache at the same time as your data store, so you can provide a completely consistent, coherent cache, even though you're doing all these different things at once. So memcache is very powerful in that way, because it has atomic guarantees. So it's definitely interesting how that works. So I think, yeah, so let me show you this in action. I have a browser here. Okay, so here's a counter. So type in hello. So get the counter. Okay, it's 1, 0, 1, 2. Right? So let's just keep reloading. And it counts. Now, I have the data viewer for this application right here. So the data viewer was empty before. So now you see hello. So first, as the counter config, you see number of shards is 1. So now I can go into this entity, and I can actually modify it, make it so it's 10 shards. Okay? Save it. Then if I go back to the counter, you see there's just 1, hello 0. Now if I go here and I start incrementing again, sit here and increment, let's see how fast I can do this. Oh, 15, not very fast. So now if I go back to here, you see there are multiple shards. And so the load is getting distributed over the shards all at the same time. Okay? So that's what we're doing. And each one of those is a separate entity group that works independently of each other. And that's what gives us that write throughput. So let's talk about building a blog. So this kind of represents many use cases. This is your blog. This is like a newspaper website, content management system. Kind of all of these use cases fall under this idea. And there are a few anti-patterns here too that people have kind of encountered. So let's make a standard blog. Let's say we have multiple blog posts. Blog posts, with the title and some message data. We want to have, for every post, we want to have a set of comments. And then we want to have paging. So paging is like, I'm looking at the latest blog posts, the first 10. Then I want to look at the next 10, and then the 10 after that, and so on. So page 1, page 2, page 3. Very common to every blog. And we want to page efficiently. So this is another anti-pattern. People in our Google group, they're like, oh, I need to page through my data. I need to look at 10 through 20, or 20 through 30. And if you do it wrong, you can use offsets, which kind of offsets your query. But remember, a big table doesn't know how many entities you have. It has to go through each one to find the entity you're looking for. So it's an O of n operation. So using offsets, we have to go through the query and then offset to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And that's where we'll start the page and then give you the results. So it's inefficient. So we want our blog to do paging efficiently. How do you do that? That's what I'm going to get into here. So the way to do it is to give blog entries an index. Okay? So an index is, for every blog entry, we give it a number. It gives it an order. It lets us establish a rigid order. So we have blog post number 1, blog post number 2, blog post number 3. We know what order they have to be in. And that lets us do efficient paging with the data store. I'll show you how that works. But remember what I told you when we started. Use the data store to your advantage. So what we've done here is we figured out a way to express paging in terms of data store queries. And that's what makes it efficient. Now, some of you might say, oh, well, it's a blog with an index, and that index is increasing. And the index has to be unique. And that's a global counter. Just like the example we showed, that's a problem, because you have a counter for the blog index that's increasing. But it's okay, because I thought about my write contention. I thought about my writes. And I realized that I might only do 10 blog posts a day. So I don't have a high throughput of writes. So that's fine. I can have one global counter. It's okay. So there's no contention, so it's not a problem. So here are the models. We have a global index. This is just a counter. Then we have a blog entry. It has the index that's been assigned to it. It has the title of the blog entry, and then the body of the blog entry. It's very similar to the shout-out example that you've seen. The difference is the index, okay? So this is really complicated. I'm going to get into this. So just take it in slowly. I'll explain. So let's say we want to post an entry. We pass in the blog name, pass in the title of the post, and we pass in the body of the post. Then we define a transaction. So first, the transaction grabs the blog index entity, and it creates it if it's not there. That's what this is. Blog index equals none, then create it. So then we grab a new index. So in a way, the blog index is saying, here's the maximum index we've seen so far. Here's the highest index that's available. So we grab that index as the next available index, and we assign it to our blog entry. So we take that next index, we increment it, and then put the index back in the data store. Then we create a new blog entry with that index, and with the title and body that have been passed in. That's this line right here. And then we put that entry into the data store. And this is all done in one transaction. So if it fails at any point with a blog index put, or with a new entry put, we start again, we try again. Now what's really interesting about this, and the hard part to understand here, is these two lines. So key name and parent. So key name gives this entity a unique name, and that's in Bigtable, in the hash table. It's a unique way to identify this object, and that lets us retrieve it from Bigtable very quickly, because it's a hash map, it's a hash table. The other thing is the parent. We set the parent to the blog index. Now if you remember, parents are how we define entity groups, and that's how we define transactions in App Engine. So by specifying the parent, we've said that the blog entry and the blog index are part of the same entity group, and thus we allow transactions across them. So that's what we're doing. And so the data actually looks like this. We have a blog index with a series of entities underneath it in a hierarchy. And this is one entity group. And that's why we can do transactions. So to get an entry, we use Bigtable like a hash table, like I was saying. We say get by the key name. Here's the parent, and here's the blog name. So if your blog name is Brett, then Brett index, Brett 0 might be your blog post, and you return it. This is really fast. This is what Bigtable's made for. So if you can structure a query as a get like this, using get by key name, or get, that's the fastest way to get data. So this would be used in the case of like a permalink, like a permanent link to this blog post by this name in a blog post number 1. That would get it really fast. Now, to actually page, this is the code. I'll step you through this also. So remember we have this index. The index is unique for every entity, and the index is increasing. So newer entities, newer blog posts have a higher index, higher number. Okay? So the first part of this, we come in and get entities, we take the starting index. Where do we want to start? So let's say at first let's say none. Just start at the beginning. That's what that means. So we do a GQL query, which says, give me all blog entries ordered by the index in descending order. So give me the highest index first, so 10, 9, 8, 7. Give me those ones, okay? And so that gives us the newest ones first. Otherwise, if we're given an index, then we change our query to have a where clause. It's an inequality filter. So to say, start at index number 7. So then give me every blog entry at index number 7 or less, ordered in descending order. So you see how that pages? We have this index for every blog entry, and then we can offset really quickly to say, oh, start at page, start at index 7, start at index 5, and then just give me what's there. So that's how we can efficiently page through there, because we've structured this as a query. And then this last kind of thing, you'll see there's post per page plus 1. So let's say we want 3 posts per page. That extra one, what does that do? Well, it lets us know, do we have another page? So if the number of entries you got back was more than on a single page, then you know there's another page that's after this one. That's all that is. So then we return back, yes, here are 3 entities on this page, and the next one on the next page. So I got some random posts from people on Google I/O posted here. So we've got our permalinks. So this is like blog post 18. Okay. Then I can leave some comments. So 1 second. So that's how comments work, and we'll get into how the comments work in just a second. But you can see I can page through this. So next page starting at 16. See this? So see start 16. Next page starting at 14. Next page starting at 12. And it's really efficient. It goes really fast. Okay, we can page all the way back. That seems really simple, but this is something people have a lot of trouble on in our group, just thinking about paging, because they're so used to SQL, which can just do it. You say, give me this page, and it just does it, because it understands count. So you have to think about things a little differently to scale with App Engine. So that's a straightforward one. It gets harder. So comments. Let's say that we want to have comments. You post a blog post, then you want a lot of people to comment on that blog post. So how does that work? Well, you can't use a shared index. When you post a blog post, you get 100 comments in just a few minutes. You get a lot of people kind of coming to your site and looking at it and participating. So you can't use a shared index. You can't use that index to guarantee a rigid ordering. Okay? So what do? Well, the first thing that comes to mind is, well, comments come in order. They come in some date order. Okay? So people have to come to the site. There's some idea of time. So let's just use the date. Well, that doesn't work. Dates aren't unique. And at Google and any kind of large-scale system, we have thousands of machines. We use NTP, like the Network Time Protocol, to synchronize them. But it's flawed. It's not perfect. Time is different on every machine within some error. So it's possible to get posts in the future and the past. Post dates aren't unique. So you can't rely on time to establish a rigid ordering. So I'm illustrating the point here. So let's say we query for our comments. On the left is the timestamp when it was posted. So 2008, May 26th at 10:11 p.m. In 4 seconds. Okay. So we have the comment on the right. Before my post, this is another post. Okay. So we do a query. These are in descending order, showing the latest one. So the latest one first, or well, it's in the order. Oh yeah, with comments, we want to see the first comment, then the second comment, and the third comment. Okay. So we show them in date order. We do a query. We get the first 3 plus an extra one to show us what's on the next page. That's what's in yellow. That's the extra. But let's say that we did a query with a page starting at this timestamp. So 10:11:04.1234. Let's do that query. This is where they would start, because the timestamp's the same. So your pages would be all messed up. It wouldn't work correctly because you don't know where to start your offset. Okay, that's kind of a subtle point. But that's a bad experience. If you see the same comment 3 times because you've gone through pages, you don't know what to do. And there's actually a lot of situations where it'll completely break your page. If you have 10 comments at the same time, and you show 10 comments per page, then your site's just broken. You can't page. So how do you deal with this? So what you do is you create a rigid ordering. Okay? So we're going to make our own composite property. Now this property is going to contain the post time, just as before. It's going to contain the user ID of the person who did the post, and then a unique ID for the comments. Okay? And so then what we'll do is that each user will have their own unique comment index. So when I post a comment, my first comment has ID number 1, my second comment has ID number 2, 3, and then 4, for just my comments. Okay? And my index for my entity and my index variable is just for me. It's my entity group. So everyone else who's commenting has their entity group too. So that scales wide. We have a different entity group for every person who wants to comment. And then what we can do, by combining these into a composite property, we can guarantee an ordering. So look at this again. I have the date time, the timestamp, who did it, and then the comment ID. So we do a query here, and we get back the extra one, which is highlighted in yellow. Now you see there are ties. There are a bunch of comments that are at 4 seconds, 0.1234. There's a bunch of them. But if we did another query after this, starting at 1234, rotting 4, that's where we'd start. There are no ties. It's a unique, rigid ordering for the data store. Now, the key takeaway here is that if you can think of your problem as a rigid ordering problem, you can solve it with App Engine. Generally, okay? And you can transform your problem into a rigid ordering problem. And that's how our queries are efficient. That's what big tables get at. Besides just being a distributed hash table, we're very good at doing rigid ordering searches, okay? And now this data looks like this. You have a user index with their comment index, and then each comment under that. And these are separate entity groups with separate transactions. And so that's why it scales. High throughput, high write throughput. And then you get a consistent view when you do queries across them. So I can show you this happening. This is in action also. So go to the post. One of these have a lot of comments. So, okay, so if I go here, there's my comment. I can say from Brett. This is comment number 2. And I can say from Brett, comment number 3. And you'll see this will go on the next page. And then I click on that, and then it'll start at the next page. And the URL, you see, kind of looks funny. It has the timestamp and some other information. Then you can clean that up. There's a lot of different ways you can clean that up. I'm just trying to be explicit so you understand. Okay, so this has been long and complicated. I understand that. I really appreciate you guys coming here and kind of coming through this with me, because it's very difficult. I understand. So what to remember? What should you take away from this? Again, this whole presentation from Google I/O is online. I think they're recording them, so we'll have this online also. The slides are online, so you can take another look at this. So if you need to look again, please do. There's some really interesting points here that are really important to understand, so please try to take it in as much as you can, and realize it's going to take some time. We're constantly writing articles, improving our documentation, doing presentations like this to educate our users as to how they have to use App Engine and our data store to make scalable apps, because we realize that it's very different than what you're used to. So, what to remember when you're building large-scale applications? So, minimize Python runtime overhead. This is just a simple one. If any other language, any other serving platform is the same way. Minimize overhead, minimize waste. Use every entity you receive. Structure your queries to maximize your efficiency. Another one is, why do a query when you can do a get? Bigtable is a distributed hash table. It's super fast. That's what it's best at. If you can make your problem into rigid ordering, that's great. But if you can make it into a get, that's even better. That's the fastest. And then the biggest takeaway, structure your data to match your load. Think about your write throughput. Think about your entity groups. Optimize for low write contention. Because if you don't, you'll get failures. You get transactional failures, and your site will fall over. We help you scale, and we help you scale very quickly and very easily. But there's still a lot of things you can do there are mistakes you can make that can impair that scaling. And so that's what I'm trying to highlight here, those anti-patterns and ways to get around them. So please think about your write throughput and think a little bit ahead about what you need to do to ensure that you can scale. And then the big thing is Memcache, the other big thing. Memcache, we have a safe API for everyone. It's awesome. It's really awesome. It's very difficult to configure if you are outside of App Engine in a lot of cases, just like setting up SQL Server and a lot of this stuff. We give every application Memcache immediately. And that's a huge win. It's just configured, ready to go. You don't even have to think about it. You just start using it. So use it. It's amazing what you'll be able to speed up with it, the amount of work you're going to save. That also means you're going to save quota. Ultimately, you'll save money when we have billing. So caching and performance are a huge aspect of implementation here. And if you want to learn more, go to code.google.com. We have all of our documentation there. We have links to videos. We have a lot of example code, articles, documentation, all that, so you can go there. Yeah, that's it. So I think we'll do some questions after this. Do we have another mic? No? Leave it that way. Okay. Hey, okay, so I'm going to use this thing. It's kind of funny. So any questions about the material so far, or any other App Engine questions?
With this very lot of service, do you have any quota limitations if I want to use it as a backup, database backup service? I transform some of my relational database into your big table. Do you have any quota limitations?
So right now we're limited to the free quota, which is 500 megabytes of storage. And so that you're limited to that. You can use it for whatever you want though, whatever you're building your application for. So we don't limit what you do with it. Outside of, I guess like very strict legal concerns, but it's up to you what you do with your quota and your application. And then, when you finally are going to be able to buy more quota, it's the same thing. We don't put any limits on what you do with App Engine. You get to build the application you want. So, okay.
Hi, Brett. I'm Chris from E-Tree. I would like to ask a question about once you use the App Engine to develop your web application, since user-generated content will host it in Google's site. So do you provide any API for application developer to get user-generated content for offline analysis?
Okay, so you want to do offline analysis of user-generated content. That's what you're trying to do. So I guess that's kind of a general. It is more of a general question. Do we have offline processing? I guess do you want to look through all your user-generated content, or take a YouTube video and figure out all the videos that link to that video, or whatever you want to do, some kind of algorithms, that kind of stuff. So right now we don't have offline processing. We specifically are aiming at request-based, database-backed applications. But we know that people want offline processing. There's a whole class of applications that you need offline processing to solve. And so we're working hard on getting you guys that. But right now we're focusing on request-based web applications. So I can't give you an ETA when we'll have offline processing done, but we know that people need it. But I will say that there's nothing that's preventing you from using other tools to do offline processing. There are a lot of open source tools and some other companies out there that have services for doing offline processing. They all work together. It's just the web, So you can pull your data out, you can do your processing offline if you want to. That's kind of the best answer we have for you right now. But we're working on a better answer.
Thank you, Brad. It's a very good talk. I just want to make sure my conclusion. My conclusion is that following those slides, since the DB store is distributed object storage, so the problem you mentioned is the problem of distributed storage. Is that right?
You mean like some of the scaling issues I explained, like write throughput, contention, those problems.
Yeah.
So I don't know if there are kind of general issues with any data storage, but for all the functionality we provided for you, in terms of consistent queries and high scalability, distribution, failover, that's the constraints of our system, yes.
So since many programmers are spoiled by the common database system like PostgreSQL or MySQL, so it's very hard for the programmers to stick like that.
Right.
And so you wanted us to manage key ourselves.
So you can manage keys by yourself. We also do assign automatically a unique key for every entity. So you don't have to, but you can. It's just an optimization. So there's no restriction there. Every entity does have a unique key. You don't have to think about it unless you want to. So that's up to you. You get to pick the unique key if you want. Otherwise, it's just an ascending number. The kind of important thing there is that, yeah, it's not PostgreSQL. It's not MySQL. It's not SQL. It's got very different characteristics and has very different performance characteristics. So it kind of takes a while to think about things differently. And so I encourage you to take App Engine for a spin, download the SDK, and try to implement something with it, and try to really do it yourself, because then you'll understand, I can't do this. Why not? Well, I have to use a different tool. And so we're trying to provide the other tools to still have the same functionality.
Actually, I think it's great.
All right, thank you. Thanks. Yeah. Right there.
How much time do we have? One more question? One more question. And it's Eric here. And I have a problem in my App Engine application. Since App Engine doesn't provide the like operation in a jQuery. So if I want to query like ABC person, I change the query to A bigger than ABC, and A is smaller than ABCZ.
Right. So
as long as I use the inequality, the order by clause just can only allow I order by A column, and it cannot order by other column. What's the solution about it?
So I understand. I think I understand the question. There's some data store operations like that. So you want to say, give me this data like this, capital letter, lowercase letter, I don't care. Right? Yeah. One of the things that we do at Google all the time, it's kind of a funny thing, but we just throw more storage at the problem. Okay? So we say, all right, well, I'll just store it twice. I'll store it all lowercase, and I'll store it in uppercase format. So then you can search for it in a canonical way, and then you can retrieve the actual data in the real way. So you can add properties all you want to your schema, however you want to do that. And so that's kind of the simplest way to get it to work right now.
So he's asking about the fact that you can order only by the field that you use the inequality.
Yeah, and so that, okay, so there's two parts to that. And then, so the other thing is, this is a fundamental limitation of big table. And you remember how I talked about, if you can translate your problem into a rigid ordering problem, you can use our system. It's not just a requirement for performance, it's a constraint. That's how we scale. And one of the things that you hear, which is kind of funny, is that if we can't do it efficiently, we kind of don't let you do it. So we give you tools that will scale, and we don't give you tools that will not scale. And so rigid ordering problems like this will scale, and ordering by the inequality property scales. Doing other kinds of things require a lot of in-memory sorting and filtering that cannot be done efficiently. So that's kind of the answer. But hopefully one of the things that we'll be able to do in the future for stuff like this is kind of like, you want to be able to do a more complicated search through text. So full text search is something that people have asked for us, a feature they've asked for a lot. You can search for entities that look like this. And then, equality operators aside, ordering aside, look at something like this. And that's a feature request that we understand that people really need, and I think that would address maybe your concerns. So I don't have, again, we don't have an ETA on that, but we're aware that people really want that.
Thank you.
So I think that's it. We're going to be at the Code Lab from 1:15 until 4 p.m., and then we'll be mingling, I think, in this room at 4 p.m. So if you have any questions for me or Pete, please stop by. We'd like to talk to you, and thanks a lot for coming. Really appreciate it.